Hello, my name is Patrick. Welcome back to another video. Today we'll be looking into time series forecasting using LSTM, which stands for Long Short-Term Memory Neural Network. More on that later. The events which we're trying to forecast are future weathers, which means we're going to be needing a data set. Lucky for us, we have access to Jana Climate, which is right here. So Jana Climate is a weather time series dataset recorded by the weather station of the Max Planck Institute of Geobiochemistry, located in Jana, Germany. And yes, I did look that up. So the dataset is made up of 14 different quantities, such as temperature, pressure, humidities, wind speed, and so on. It covers data from January the 1st, 2009, all the way to December the 31st, 2016. So before we start, I just want to let you know that I've linked the repository and the download link for the dataset in the description section of the video. So if you want to pull my code and play around with it, you are more than welcome to. And if you're looking for any instructions, you can refer to the README. For example, if you're looking to setting up the environment or using the prediction model. Okay, without further ado, let's get started. So this time, I already have the implementation done, so I won't be coding from scratch. But of course, I'll still go through and explain my thinking process. Okay, so first of all, we're going to be importing our dataset, which is a CSV file, as you can see from here. So to do this, we'll be using Pandas, which is a Python library used for data manipulation and analysis. We'll read the CSV file into a data frame. So what is the data frame? So DF stands for data frame. It's kind of like a table or a spreadsheet. Let me just quickly show you what it looks like. So we're going to be doing print data frame dot head. So it means the first 10 items. Okay. Okay, so this is what it looks like. You see, even give you the row numbers as well. So you have the date time and the metrics like pressure, temperature, wind speed, max wind speed, and the degree, which is the direction which the wind is blowing. You have a bunch of metrics in the middle which are omitted, but just know that they're still there. So you can see that for the daytime, the data is captured every 10 minutes. So in my opinion, I think going by interval of 10 minutes is a little bit unnecessary for our purposes. So instead, we'll be doing it for every hour, okay? So for data frame, it supports slicing. I have the syntax written right here. Go start, stop, and step. So we're going to start from index 5, which is right here, exactly at 1 o'clock. And we're going to stepping by 6. Why do we stepping by 6? Well, that's because there's 10 minutes in 1 hour. So if you go by 6, you're going to go by 1 hour, 2 hour, 3 hours. Okay. Besides just the slicing, we're also going to be converting the date time, which in this case is actually just a string. We're going to be using Panda to convert it into an actual datetime object. So PD dot to datetime. You also have to pass the format right here, and the reason why I have to do this is because it's kind of irregular, the format. So if you want Panda to know which number stands for which, instance of the metrics, you need to pass the format parameter right here. Okay, let me show you what it looks now after slicing has been done. Comment this line out. Okay, so you can see now, instead of going just by 10 minutes, it now goes by 1 hour. 1 hour, 2 hour. It also gives you the row number, of course. So 5, stepping 6 to 11, stepping 6 again to 17. And any other rows that's in between are simply cut off. Okay. So the dataset came from a professional laboratory, which means it is super clean. Minimum work required to clean up. However, there are still outliers, specifically on the instruments that's measuring the wind speed. Let me just quickly show the error. Let's uncomment these two lines out. Let me explain them really quickly. So we're going to print data frame of the wind speed. So what does this stand for? It means we're extracting the column, the wind speed column. So it's one row of data going down, and we want the minimum value. And for this, we want to extract the max wind speed column. and we want to take the minimum value. Let's go ahead and run it. Oh, sorry about that. I did not mean I shouldn't print the head. Sorry about that. Okay, but you can see right here. So we have these. So negative 9999, negative 9999. That doesn't make sense, right? Because wind speed. Wind is either blowing or not blowing, which means the value has to be greater or equal to 0. So this shows that it's an instrumental error. So how do we fix this? Well, my solution is to simply set them to 0 if the instrument is having an error. Okay, so we're going to say wind speed equals to extract the wind speed column. And then we're going to say bad wind speed equals wind speed equal negative 9999, which is the error value. So what does this line means exactly? It's actually two parts. So this is the first part, bad wind speed equal to assigning a value or an object to the bad wind speed, I guess, variable. And this is the second part. What does this mean exactly? It means for any of the blocks or rows in the wind speed column that equals to 9999, we're going to take it out and assign it to the bad wind speed. Okay? So when I do wind speed, which is the wind speed column, and pointing to all of the blocks that are having the bad wind speed value, we're going to set all of them to 0. Make sense? Okay, and we'll do the same exactly for the max wind speed column as well. For any of the blocks in the column that equals to negative 9999, we're going to set them to 0. Okay, so after the cleanup, let's go ahead and print and see what is the minimum value in all of these two columns. Comment that out. Oh, we did. Okay, good. Okay, now it equals to 0. We no longer have negative wind speed. And for me, this is good enough. All right, next up, let's move on to data preparation, which is going to be used for building our model. So before anything, we're going to import some libraries. First of all, import our operating systems. Next up, we're going to import NumPy as NP. We talked about this last time, used for manipulating tensors and matrices and stuff like that. We're also going to import from scikit-learn processing for our standard scalars. This is going to be used for normalization. The reason why we're using a external scalar instead of just dividing numbers by ourselves is because this data set is much more dynamic, right? There's a lot more numbers, significant amount of data that need to be fed into the neural network. And unlike last time, which is just RGB color divided by 255, it's a little bit unmanageable. So I'm using an external function to do it for me. And also importing our data frame variable from import SCVC, which was just worked on. This line right here, operating system.environ, is just used to suppress our hardware warnings when we're training our models. Okay, so the first thing we want to do is to slice off the datetime column. The reason for that is because when you're doing time series, you want to predict the future. You don't care about the dates in the past because you're not trying to go backwards, predict the past. So we're going to be using slicing. So we want to start and stop. So we want to start from the first index, which in this case is pressure, because datetime is at index 0, okay? And then 15. So 15 is exclusive, which means we're going to be including the 14th column. So we're going to say 15 here. Let me print it out for you really quickly and show you what it looks like. So there you go. So we start from pressure, and we end at wind degree, which is the pressure, which is the direction of the wind. All 14 metrics, all here. Only thing we're missing is the datetime, which we've purposely cut off. Okay, next up, we're also going to be converting all of the data for the metrics into floats. So when it's in CSV file format, all of these are in strings, but you can't really scale strings, so we're going to convert all of them to float and store them in something called data frame for training. So this is the scikit-learn standard scalar that we've talked about. So the purpose of a scalar or normalization is to scale down the size of the data. So you don't have gigantic numbers and super tiny numbers that it's difficult to work with. Because when you feed them into a neural network, data that are in a normalized state, so smaller than this original state, it's much easier to train. It's not just accurate, but also save you significant time for building the model. So first of all, we're going to initiate the function. We'll say scalar equals to standard scalar. Then we're going to port our data into the scalar. So we'll say scalar.fit df for training, which we've converted all of them to floats. And last but not least, we're simply going to do scalar.transform and the data. That's it. Really simple. Let me go ahead and print it out for you. Okay, we have it right here. So before, you can see in the data set, I think there's like some numbers in the thousands. So right now it's much smaller. You have 0.2, negative 2, negative 2, negative 2.12. So much more manageable for during the training process. Okay, so next up, we're going to be populating our lists with training data and validation data. So train X is going to be used for storing the training data, and train Y is going to be used for storing the validation data. So the idea of the validation is that after your model has read through a certain number of data, it's going to take a guess, make a prediction, right? So the validation data serves as a ground truth to see how far off or how close the model is to the actual correct data. It would then make adjustments based on it. Okay, so my design right here is that I'm going to read 14 days worth of data, or in this case, it's going to be 14 hours worth of data, and then on the last hour, I'm going to make a prediction and then validate it with the actual hour on the 15th. So to populate the two lists, I'm going to use a for loop. So for I in range of the impasse, which is 14 periods, and the length is going to be the total. The stop is going to be the total length of the data minus in future, which is 1, and then I'm also going to plus 1 to fill the gap. Okay. So I'm going to, and then this is where we build our tensor. Okay. Actually, before I do this, I should show you the shape of the training set. So I'm going to say print df for scaled dot shape. Let's go ahead and run that. So it has two components. The first one is the total number of points, the data points, right? In this case, it's actually just rows. And the second part is the number of metrics. So this is the column number. So 14 columns in total. Okay. So I'm gonna say for the rows, I'm gonna say so I minus the pass. What is I? Well, I starts on impasse, right? So right now, impasse minus impasse is just index 0. And what am I going to stop on? I'm going to stop on I, which is impasse. And for the second part, which is the column number, I'm simply going to pass it the shape of the original data set. How many columns we have in the original data set? 14 metrics, right? So we say 14, right? Shape 1. Take another look really quick, right? 14, index 1. And for the train Y, which is our validation set, we don't care about the shape or the column number because we only just want one number, the prediction number, right? So we're gonna start for the column. The row is gonna be I plus in future, which is gonna be 1, which is gonna be after the training, after the pass, which is the training set. I'm gonna minus 1, and then where do we stop? We're gonna stop exactly 1 after. So we're just simply gonna do I plus in future, right? No problem here. So after populating them, I'm also going to go ahead and then turn both the training sets and the validation sets into NumPy arrays to feed them into the model. Let me quickly show you what they look like after, with the shape of them after you populate the two lists. Okay, yeah, so the parameters, total parameters does not change, okay? And I'm going to say 14 by 14. What is this? So we have 14, which is right here, by 14. You go by a step of 14, and you have the metrics, which is 14. And then for our Y shape, we simply just want one prediction data, right? I hope my explanation is clear. I know this is a little bit confusing. You can play around with it later if you want, or let me know if you need further explanations. Okay, so I was recording, mid-recording, then I realized the font size is super tiny and it might be difficult for you guys to read. So super sorry about that. I've readjusted the font size, so it should be much more readable now. Okay, back on topic. So now we're building our model. Some dependencies first, so import OS. From Keras, import models. From Keras, import layers. So Keras is the official high-level API for TensorFlow. If you have installed TensorFlow already, Keras library should be automatically available. And we're also gonna get our training set and our validation set from DataPrep. Okay. OS environment just to suppress the hardware warnings when we're building the model. We've talked about this before. Okay, so the models we're going to be building is a sequential model using the LSTM neural network. LSTM, which stands for Long Short-Term Memory Neural Network. So it really excels at capturing long-term dependencies. So making it really ideal for sequence prediction tasks, which is exactly what we're trying to do. In our case, it's time series forecasting, predicting weathers in the future by using past data. Okay, so first of all, we're going to add our layers, our LSMTM layers. We're going to start from 128 units, activation 10H. Last time we used ReLU when we were doing our facial recognition stuff, but this time because it's raw data points, we're going to use something a little bit more more concrete, more solid, less leniency. So 10H, it's much tighter when it comes to restrictions. Our input shape is going to be 14 by 14. Remember what the shape one is? It's the steps which we're going to be crossing when we're traversing the data set. So 14. And for shape 2, it's the column. So we have 14 metrics in total. So 14 by 14. Okay. So return sequence. This is something special about LSTM. It allows you to propagate the traits which you have collected onto another layer. Typically, this is not done with most neural networks, but LSTM allows to do it. The idea here is that you're able to remember the traits from a very long time ago, which you've predicted or have collected, which makes it really ideal for predicting weathers in our case. So we're going to say true here. For our second layer, we're doing half of the units, so 64, 10H, nothing changes, return sequence to true. So we're going to propagate the traits we've collected here onto a third layer. So third layer is going to be 32, 10H, and we're going to say return sequence equals to false because we don't want the trace to propagate onto additional more layers on our dropout or dense layers. Okay. So for the dropout layer, we're going to say dropout 0.2. So what does this mean? It means after each cycle or each epoch, we're going to throw away 20% the data we've collected. The idea here is that to further, I guess, blend our data. So during the training process, it will make it more accurate since we're throwing away a portion of the batch each time. This will mean that the training time will be slightly longer, but theoretically, it should also make the model not overfitting, which is what we want. And last but not least is our dense layer, which is the output layer. We only want a single prediction, so we're going to say train y shape 1, which if you remembered is just 1. Okay. Now we're going to do model.compile. For the loss, I'm using mean squared error, and for the optimizer, I'm using the Atom optimizer. Okay, let's go ahead and take a look at our summary. Okay, so we have 1, 2, 3, 4, 5 layers in total. So for the first layer, we have 128 units or filters. Stepping 14, and the second layer is 64, stepping 14. And for our third LSTM layers, because we're no longer propagating, no longer using return sequence, we're no longer be stepping, so we're just 32. Okay. Our dropout layers 32, the same. And finally, our dense layer, we have one single output. So our total parameter is 138,000. So if you remember from our previous project we did about the facial recognition, we have around 7 million parameters. So this is much less. So the training process should also be pretty fast. Okay. So we're now going to fit our model. So we're going to say model.fit. Train X is going to be our training data. Train Y is going to be our validation data. Our batch size, which is how many how many data points, how many rows of data we're going to be throwing into each batch. We're going to say 32 rows. Epoch, we're going to train for 20 cycles. So each epoch is one complete go through of the entire data set. Validation split, this is used for cross-validation. We already have our train Y, which is for validation, but we're going to also use 10% of it for cross-validation. And verbose 2 is to get some additional information when we print them out during the training. And of course, before you actually fit the model, make sure you actually save it so you don't have to do it for a second time. Okay, let's go ahead and then run it. Okay, let's wait for the procedure to get started. Okay, so the first cycle has begun. This is going to take around 3 to 4 minutes, so I'll cut the video to it when we finish this training, okay? Okay, so our model has finished training. If we take a look at the last few epochs, so let's say from 70 to 20, our loss on the data is sitting at around 1.1%, and our validation loss is sitting around 0.2%, which is pretty good. Okay, so if you look at our file directory right now, we have models, a folder, and the models that's sitting inside, which have been stored right here. Okay, so now we have our models. We can go ahead and then try to forecast our future weathers. All right, we're now ready to forecast some weathers. Okay, so go ahead and start with our dependencies. So import our operating system, import our system module, import NumPy as MP. We're going to import our datetime from our import CSV. We're going to import our training xset, the scalar, and also the data frame used for training from data prep. We're also going to import our modules from Keras. The module is going to be used to, again, open the model we've just built, and also import pandas as PD. OS-Enviro is going to be used for suppressing the warnings during prediction. Okay, so let's start by porting our models over. So we're going to say models.loadModel, os.path.join, models, which is the folder we have right here, and model.h5 is the file name. Okay, so first of all, we're going to have to decide how many periods we want to predict into the future. So for me, I'm going to do 7.5 years times 365 days times 24 hours because our data is advancing one row every 1 hour, yes? Okay, so the reason why I didn't do more, let's say I want to do 20 years or 30 years, it's simply because the more periods you're planning to predict, the longer the prediction period it will take for the GPU to compute. And I mean, I find that kind of unnecessary since, I mean, our project is going to be done at the in the half of the 2024 year. So if we do 7.5, it's going to end around June of 2024. Okay. So our forecasting period hour is going to be our pandas dot date range. We're going to start from the last date of the original data set, right? Index -1. So I think it's around December 31st, 23 hours, so which is the last day of 2016. For the end future, we're going to predict 7.5 years into the future, and the frequency is going to be 1 hour. Convert that to a list. Let me show you what it looks like really quickly. Let me comment that so it doesn't go through the prediction. Oh shoot, I just realized I'm using the prediction. Sorry about that. I actually need that. Okay, run through it. Okay, so after predicting for 7.5 years, we ended on June 30th, 2024 at 10 o'clock. Okay. So now we're going to go ahead and use our original TrainX to predict in the future. You may be asking why I'm using the training data to predict in the future. Well, that's because it's a time series. You use your old data from the past to advance into the future. So I'm using TrainX. How many days I'm using from TrainX? Well, I'm using the same number of days I want to predict in the future. So I do a negative index, which is the last 7.5 years from the original data set. Okay, I'm going to go ahead and show you what it looks like after the prediction. Remember when we did our model, it's just going to be one number per prediction. So it's actually just going to be one list of just individual one block predictions. Now, as you can see, it's just one number per block. So this is the prediction, 1.13, 1.37, negative 0.01. You're like, what is this? How is this weather data? Well, we'll look into it. Okay, so first of all, we know that the data we have right here is still in the normalized state, right? Because if you remember when we did our data prep, we normalized our data by using the scikit-learn transform function. But now we want our original data back, the actual, the numbers for the data. We have to inverse transform, which is this. However, because we only have one single column of data, and the original data set is in 14 metrics, we're going to have to print our column 14 times and then inverse. So which is why I did right here, numpy.repeat prediction, which is our prediction. How many times do we want to repeat it? 14 times. That's why we do df.training shape1, which is 14 metrics, x is -1. And then we can inverse our original data set, our prediction into what it looks, what it's into a readable data set. Okay, so show you quickly. Oh, sorry about that. Go ahead and do it. So whatever is going to get printed out here, it's going to have 14 metrics, which is what we want, and it's also going to be in its original state, original units, a non-normalized state. Okay. Okay, look. So we have pressure at 1,000, degree 20 in degree, and then Celsius at 294. Now this is much readable. We have wind speed here as well, and with the direction 287 degree. It's very good. All right, now we have our readable data. We're going to go ahead and store them into lists. Okay, so forecast hours, this is our timestamp, and the rest are the 14 metrics that we've talked about, like pressure, temperature, wind speed, wind direction, etc., etc. So we're going to say for x in range, the length of the forecasting period hours. So this is 7.5 years worth of hours that we've previously set. We're going to store the hours into a list called forecast hours. And for the rest of the 14 metrics, we can do the same. And the reason why this is the same is because we know that x, the index align with each other. That means the first date or the first hour is also going to have the pressure which it corresponds to. The only difference is that y prediction future is a two-dimensional, which means x contains 14 metrics of the first hour. So if we just want the pressure, we're going to do 0. So iterate from 0 to 13. Okay. So now they're all stored in individual lists. We're going to go ahead and port them into a Panda data frame. The reason why we put them into a data frame is because the data frame supports search functions. So make it much easier when we want to extract that specific row of information later on. Okay, so these strings right here are simply the column name, which I've given them. They're based on the name of the metrics exactly. And the only thing we have to do is to provide them with a list. And that's it. Of course, we're also going to convert the date time column into an actual date object, so it'll be easier for us to extract information later on. Okay, and last but not the very least, we're going to write the information onto a text file. So we're going to say with open output.txt, that's the name you want to give to your text file. Write operation as f, so file. For x in range 1 len sysarg. So what is this? Well, when you do a command line operation, when you want to run a Python program, you can provide it with arguments, called system arguments. So we start from the index 1 argument. Why not index 0? Well, that's because index 0 is always going to be the name of the file. We don't want that, right? We want index 1, which refer to the second arguments. In this case, it can be a date. This is inclusive. And where do we end? We end on length system args. We end on the length of the arguments. Again, this is exclusive, which means it will not be counted. That means the index is referring to len minus 1. Okay? Okay, so how do we search in a Panda data frame? We're going to do your data frame dot locate provided with the column name equals to the arguments. In this case, we're search for a date, right? So we do datetime equal to system args, and then we're going to iterate through the arguments because we're going to provide with multiple arguments. We can extract multiple dates we want in one go, okay? And then we're going to write them onto the file. So we do file.write string weather prediction, which is the row we've extracted. We only want that specific column, right? So we do datetime pressure provided with individual names. What is dot value 0? This is only the value which is extracted. If you do not provide dot value 0, it's going to give you other stuff like the type of the variable, the row which the data that the data points is stored in. You don't want any of that. So we're going to do data index 0. Okay. And last but not least, we're going to say fclose. Yeah, so I'm going to show you really quick. I'm going to comment this out. So this is just the raw data points. I'm going to use the one for visualization so you actually get the titles. Okay, let's run it. So I'm going to use terminal. So I'm going to say Python. So you want to provide the name, forecast, this is index 0, and then we're going to provide it something else. So let's say today is October the 14th. Okay. So we're going to say 2023 110-14, and right now New York time is 6:10. So we're going to do because it's 6 p.m. So we're instead going to do 18 hours and 10-00. Okay. Okay, it's going to first go through prediction and then give us the output. So you can see 7.5 years actually takes quite a bit of time. So if we do more, it's going to take even longer. Okay, so now we got our prediction, which is stored in the output.txt file. If we take a quick peek at it. Okay, so we see the date which we're trying to predict is 2023 October the 14th, 6 p.m., 10 minutes. Okay, so pressure is at around 92 Pascal. Temperature in degrees is 2.6 degrees. Temperature in Kelvin is 276. Let's see, what's the wind speed? 0.8 meter per second. And the direction it's blowing is at 104 degrees. 2 and 4, that's actually really, really cold. Okay, so one last thing. So you're probably asking, okay, just how accurate is our prediction results? Well, the dataset is from Jena, Germany, from the Institute of Biogeochemistry. So we can actually go ahead and compare it to the actual weather info. Okay, so let's go ahead and then do the prediction. So we're gonna do, so in the terminal, we'll do Python. File name is forecast.py, and then right now in Jena, Germany, it's 2023 October the 14th at around 23:10 hours. Okay, let's go ahead and make the prediction. Okay, finished. Okay, let's take a look at our output.txt. Okay, so October the 14th, 23:10. So air pressure at 281, 1.6 degrees. Maximum wind speed at 1.35, normal wind speed at 0.69, and a wind direction at around 94 degrees. Okay, well, let's go ahead and compare it to the actual weather info, shall we? Okay, so welcome to the website where they display the weather data for the biogeochemistry laboratory located in Jena, Germany. Okay, so let's take a look how it compares to the data that we predicted. So pressure, we have 981.42. Their pressure is sitting at 989. It's pretty close. For temperature, we have 1.6 degrees. They are sitting at, for air temperature, they're sitting at 7.7. Humidity, relative humidity, we have it's 60.6%. They're sitting at 85.6%. Let's look at wind. Wind speed, we have 0.69. Their wind speed is at 1.9. The direction, we have 96 degrees. Theirs is at 273 degrees. So 90 degrees off. um, so yeah. So you may be asking, okay, why does the data not exactly match as what we're supposed to be getting? Because this is the real life data. Well, just think for a second. Have you ever heard of weather forecasting 7 years in advance? Probably not, right? It would not be accurate. It doesn't make sense. Exactly. The most we've heard is probably like say 10 days in advance, a week in advance, or 2 weeks in advance. Well, the reason for that is because it's not because time series forecasting is not accurate. It's because it requires 2 additional parameters in order to be considered as in its most accurate state. The first one is having the most recent data points available, right? Our most recent data points is from 2016. Well, that's like 6 years ago. And the second of all is that we require the predicted period to be the least amount, as little as possible. So we're trying to predict 7 years worth of data. So the error propagates. So instead, if let's say we only predict, let's say 1 hour or like 1 day, 24 hours, it will probably be pretty gosh darn accurate. That's the idea. So, however, for the purpose of our project, which is simulating the weather data, the variables we have or the data we have is very believable. So it serves its purpose, which I think is the main point of this machine learning project. Okay, so let me know if you have any questions you want to ask, and ping me on Discord if you need, and I'll see you around. Bye for now.